Problem number 6. A pendulum is made with a string and a bucket full of water. When the string is vertical, the bottom of the bucket is near the ground. Then, the pendulum is set swinging with a small amplitude, and a very small hole is opened at the bottom of the bucket, which leaks water at a constant rate. After a few full swings, which of the following best shows the amount of water that has landed on the ground as a function of position? Solution to problem number 6. The amount of water at each location is proportional to how long the bucket spends there, so it is inversely proportional to the velocity. Therefore, it is the lowest, but non-zero, at the middle, where the bucket has maximum velocity, and highest at the endpoints, where the bucket is turning around. This is answer C, and that was solution for problem 6. Problem number 7. A particle travels in a straight line. Its velocity as a function of time is shown below. Which of the following shows the velocity as a function of distance x from its initial position? Solution to problem number 7. The particle accelerates uniformly, then travels at a constant velocity for some time, then decelerates uniformly down to resting. As a function of distance, then, the velocity must also increase, then stay constant for some time, then decrease down to zero. Since velocity versus time is symmetric, velocity versus distance must be symmetric as well, which is case A, B or C. If the movie were played backwards, it should look the same. When the particle is accelerating uniformly, its velocity is proportional to t, while the distance is proportional to t square, for example, as in free fall. Consequently, velocity is proportional to the square root of distance. This is answer C, and that was solution for problem 7. Problem number 8. A rod of length L is sliding down a frictionless wall. When the rod makes an angle of 45 degrees to the horizontal, the bottom of the rod has speed v. At this moment, what is the speed of the middle of the rod? Solution to problem number 8. The bottom of the rod has rightward velocity v, so by symmetry, the top of the rod has downward velocity v. The velocity of the middle of the rod is the average of these velocities, and thus has magnitude equal v over square root from 2. This is answer B, and that was solution for problem 8. Problem number 9. When a car's brakes are fully engaged, it takes 100 meters to stop on a dry road, which has coefficient of kinetic friction mu k equals 0.8 with the tires. Now suppose only the first 50 meters of the road is dry, and the rest is covered with ice, with mu k equals 0.2. What total distance does the car need to stop? Solution to problem number 9. When the road is dry, the work done on the car by friction is equal to mu d mgx, where mu d is the coefficient of friction with the dry road and x equals 100 meters is the braking distance. This work should be equal to the car's initial kinetic energy k. In the second case we use half of kinetic energy for the first 50 meters and other half for the ice road, which is giving equation 1. So from here we have distance on the ice road is 2x. And total distance d equal x over 2 plus 2x, which is 250 meters. This is answer C, and that was solution for problem 9. Problem number 10. A block of mass m is connected to the walls of a frictionless box by two massless springs with relaxed lengths L and 2L, and spring constants k and 2k respectively. The length of the box is 3L. The system rotates with a constant angular velocity omega about one of its walls. Suppose the block stays at a constant distance r from the axis of rotation, without touching either of the walls. What is the value of R? Solution to problem number 10. We balance forces on the block in the reference frame rotating with the box. To give equation 1, solving for R gives the answer D. That was solution for problem 10.